Good morning, good afternoon, good evening, class. It's Mr. Arocena, and on today's video, we're going to take a break from chemistry for a little bit and talk a little bit about an important math concept called logarithms. Why is this important? Because logarithms are used to describe the pH scale. So the numerical pH scale is described as a logarithmic scale, not as a normal scale. For those of you who've taken pre-calculus math already, pH is a common example of where logarithms are used. Other examples are earthquake strength and sound are also logarithmic. So first things first, what is a logarithm? A logarithm is a mathematical function denoted by this notation here, log base 10x. You can get logarithms in other bases, but for chemistry purposes, we'll stick with the base 10 logarithm. So what this translates to is it says that the logarithm to the base of 10 of x. And this function will return a number that basically is what power of 10 will give me the number x. Okay, so that's what the logarithm is. The logarithm is a power of 10. So a power of 10 that gives us back whatever this number is inside the logarithm. Okay. So here are a few examples to quickly go over this. For example, what is the logarithm of 1000? We write this as log 1000. I'm omitting the base 10 because we're going to assume it's base 10 unless otherwise stated. And basically what this means is what power of 10 gives me the number 1000. So this logarithm here will give me a number. We'll call that x. And if I go 10 to the x, that will equal 1000. Okay. So here it's quite easy. It's like what power of 10 gives me 1000? Well, it'll be 3. So this will be 3. Okay. Now, here's a couple more examples you can try out. Here, for example, like what is the log of 100,000? And then on the reverse side, what is the log of 0.0005? Right, the first one I think will be, you can do it without a calculator, but the second one you can just use a calculator for that. So give it a try and then let's proceed. Okay, so this first one here basically translates into what power of 10 is going to give me 100,000. And here this will just be 3. So not 3, what am I talking about? This will be 5. Thinking about the other example. So log 100,000, this will be 5. Okay, let's use a different color. The one below it's a little more difficult because it's not quite as obvious. What power of 10 is going to give me 0.0005? Okay, here you can just throw this into a calculator. So using your calculator, okay, so using a calculator, we'll go 0.0005 and then log, and there we go. So this will be log 0.005 is equal to negative 3.3. How about that? Then you can always check it. So what is 10 to the negative 3.3? 10 power of, there we go. There you go. That is about 5 to the negative 4, which is about what we got. So that's what a logarithm does. Logarithm returns this power of 10 so that it'll give the number that's inside the logarithm. Okay. Now the reverse operation of a logarithm is called an antilog. And an antilog is basically just 10 to the power of something. So the antilog of some number is just basically 10 to the x. Okay, and what this antilog calculates is quite literally the power of 10 after you take it to whatever power is inside the antilog. Okay, so this is the antilog, and the logarithm is written as log x. Okay, and the two are related. I should actually use different variables for here, but the two are related as follows. If I go 10 to the x, this will give me some number y. And if I go log y, that'll give me x. So that's kind of how the antilog and the logarithm are related. So they're reverse of each other. Okay, sort of like addition, subtraction, or multiplication, division. Okay, so here's a quick simple example. Calculate the antilog of the following numbers. So the antilog will simply be calculated as follows. This would be like 10 to the power of 2. That's easy enough to do. That's 10 times 10, so that's 100. This one would be 10 to the power of negative 5.5. That one's a little harder to do, so we'll use our calculator for that. So 10 to the power of negative 5.5. So that'll be about 3.2 to the negative 6. And then the last one, you do the same thing. 10 to the power of 2.4. Then throw that into a calculator. 10 to the power of 2.4, about 251. Okay. Or with proper significant figures, this would be 2.5 times 10 to the negative, or 10 to the 2. So that's the antilog. So the antilog is basically you just take the number and just apply it as a power of 10. The logarithm of a number gives you the power of 10 necessary. All right. So to recap this super quick lesson on logarithms, logarithms give the exponent x in 10 to the x. Antilogs will give you the value of 10 to the x, so the evaluated value of 10 to the x. And the antilog is the reverse of the logarithm. There you go. We'll be using both operations quite heavily moving forward for pH calculations. Now, there's a couple of rules that are, if you remember them, logarithms had a bunch of laws called the laws of logarithms. There's a few rules that we are going to be kind of referencing throughout this unit in chemistry. And I'm going to restate them here. So this one is important. This is the law of logarithms for addition. And basically it states that if you're adding logarithms, they can be rewritten. So if you're adding logarithms, you can rewrite it like this. Okay. It helps simplify some things and also helps us see a few things that will make our lives a little bit easier. Okay. So in other words, this rule can be written as this. Log A plus log B is equal to log A times B. Okay. And this is I think this is the only rule we're going to be referencing. There's a bunch of other logarithm rules, but this is the only one that we're going to be referencing in this class. All right, how does this tie into pH? All right, well, there's going to be two values we'll be talking about, pH and pOH. You guys have probably heard of pH before. We introduced it in Science 10 when you guys first saw acids and bases. pOH is related, but not quite the same. All right, so pH, in order to calculate pH, this is the negative logarithm of the concentration of hydronium. So negative logarithm. Okay, not positive logarithm, negative. So this is pH. pH is here. And pOH is the negative logarithm of the amount of OH minus present in your solution. So that's kind of what they are. If you have the concentration of hydronium, you can calculate the pH, and similarly, if you have the pH, you can calculate the concentration of hydronium. Why? Why can we do that? Well, remember, the antilog of this, the antilog or the pH returns us a power of 10. So if we take 10 to that pH, that'll give us the antilog, which would give us this number back here. Okay, and we'll go through some examples of that. Here's some quick examples of how to calculate the pH. So we'll calculate the pH if the concentration of hydronium is 3.94 times 10 to the negative 3. And then we'll do the same thing for calculating the pOH if the concentration of OH minus is 3.94 times 10 to the negative 3. I realize I should have probably picked different numbers, but that's okay. The process is still the same. So to calculate pH, we're going to do the following. We'll take the negative logarithm of my concentration of hydronium, which is 3.94 times 10 to the negative 3. Throwing that into our calculator, we will get the following. Okay, so this is going to look really strange. 3.94 times, there we go, equals, and then we'll logarithm that. And because we're taking the negative logarithm, this will be 2.4. 2.4. Now pH has no units, so we'll just leave it as 2.4. pOH calculate the same way, so pOH is equal to negative log the concentration of OH minus. In this case is the same. Really should have changed that, but that's okay, which will give us the same answer of 2.4. There you go. So that's how we calculate the pH. pH is negative log and the concentration of hydronium. All right, now how are these two related? Well, the antilog, as I mentioned earlier, is the negative of the antilog of the negative pHpOH will give us the concentration of hydronium and hydroxide respectively. So if I take the antilog of the negative pH, and this is important, negative pH, not positive pH, and the antilog of the negative pOH, I will get the concentration of hydronium, which is really interesting. Well, it's not really that interesting. It's just basically a mathematical trick, kind of, I guess. Yeah. So if I were to take, for example, the concentration, if I were asked to find the concentration of hydronium and given a pH, then I can do the following. For the for this pH, the concentration of hydronium would be equal to 10 to the negative pH, 10 to the negative 3.46, and then we just throw that into our calculator. Most of these you probably won't be able to do without a calculator because I don't think we were ever shown how to do these types of calculations by hand. Anyways, there you go. So this would be 3.47 times 10 to the negative 4. So it's 3.47 times 10 to the negative 4. And then the concentration of OH, you would calculate the same way. So concentration of OH minus 10 to the negative 3.46. I really have to change my numbers next time, but that's okay. The process is still the same. Throwing that in a calculator, we get the following. There we go. So now we can see how pH and concentration of H3O plus are related, and similarly how pOH and concentration of hydronium are related. Okay. If you know one, you can calculate the other without too much difficulty. All right. Now here's some more other examples you can try for yourself. Now this one, what is the pOH if the pH is 9.45? This one is, at first, looks a little difficult because we haven't quite shown how pOH and pH are related to each other. We've shown how pOH is related to the concentration of hydroxide, and we've shown how pH is related to the concentration of hydronium. We haven't shown how these two are related, and this example is going to show us what to do in a case like this. All right, so we need a little bit more space. So here's the example. But before we can actually solve it, we're going to go talk we're going to talk about a relationship from a few videos ago where we talked about how the kW of a solution is equivalent to the following: H3O plus times OH minus. And if you remember, this kW value has the kW has the following value: 1.00 times 10 to the negative 14. So and I can sort of see, if you recall this from earlier, how the concentration of H3O plus and the concentration of OH minus are related, because if I multiply their concentrations together, I come up with this value here. How does that help us? Because we're just talking about logarithms. Well, if you recall that if I take the logarithm, so let's say I take the logarithm of both sides. So here I am taking the logarithm of the concentration. Oops, clean that up. OH minus. And then this, I have to take the logarithm of this side, 1.00 times 10 to the negative 14. I can apply the logarithm rule. I can apply that logarithm rule I mentioned earlier and say the following. So this would be the log of H3O plus plus the log of OH minus, because this is a multiplication here. I can split up that multiplication to look like this, and this will just equal the logarithm of, and this I can simplify to just 10 to the negative 14 like that. And then calculating this out, I get the following, where I get the logarithm of H3O plus the logarithm of OH minus is equal to this, which is just going to be negative 14. Now, if I make everything negative, so if I make this negative and I make that negative, then this has to become a positive, and we get this relationship, because we know this is just pH, this is just pOH, and all of that is going to equal 14. So this is a really interesting relationship where the pH plus the pOH of a solution has to equal 14. Now I'll make a note that this is at room temperature. It's actually slightly different at higher or lower temperatures, because if you recall from my when we first originally talked about kW, if the temperature goes up, then the kW value will also go up, which will mean this number will change. So if the temperature changes, this number will change and this relationship will also change. But the sentiment is still the same, in that the pH and the pOH have to equal some constant value. So we're going to assume everything's at room temperature, so we can keep this value or this equation in mind, which will then allow us to solve this example relatively easily. So if we go back to our example, we have a pOH, or we're asked to find the pOH if the pH is 9.45. Well, because of this proof here, I know that my pH and pOH added together have to equal 14. So if my pH is 9.45 and my pOH is unknown, both of them together have to add to 14. So my pOH is going to be 14 minus 9.45, which is going to be about 4.55. There we go. Now this kind of makes sense too when you think about it, because if something is more basic, then it's less acidic. And if you remember from Science 10, high pH values mean, so if you remember from Science 10, if pH goes up, it becomes more basic. If pH goes down, it becomes more acidic. Okay, and these values will correspond to higher amounts. So high pH means low amount of hydronium, high amount of hydroxide. Low pH is the opposite, where you have a high amount of hydronium and a low amount of hydroxide. Let's go do another example. So here we want to calculate what is the concentration of hydronium if the pH is 4.5. So this one's slightly more complicated, because now we're asked to find the next step. It's not so bad though, because we know that my pH and my pOH added together have to equal 14. So this will allow us to easily calculate what my pOH is. pOH will then be 14 minus pH. So altogether, I have a pOH of 9.5. Right, now to calculate the concentration of hydroxide, this is just the anti-log of the negative pOH, so 10 to the negative 9.5. Then we just throw that into our calculator. So 9.5 negative 10 to the power of that. So we get an answer of about 3.16 times 10 to the negative 10. 0.16 times 10 to the negative 10, although with proper significant figures 3.2 times 10 to the negative 10. There we go, and that'll be in molarity because it is a concentration. So there you go. So that's kind of how logarithms work with regards to pH and pOH. So to do a quick recap while the assignment's up here, pH is the negative logarithm of the concentration of hydronium. And then the reverse, if you do the anti-log of that, that'll be 10 to the negative pH. And pOH is the negative logarithm of the concentration of hydroxide. And the concentration of hydroxide is the antilog of the pOH, or sorry, antilog of the negative pOH. And then the most important relationship from all of this is that if I take the pH and add that to the pOH, this will equal 14. Or whatever the value happens to be if the temperature is different. But for the most part, we'll stick with 14. There you go. All right, your assignment is, if you have your textbooks with you, you can work on those questions. They should help you understand this a little bit better. And if you guys have any issues, you guys all know how to contact me.